This is lecture number 31 of the course ME314 Fluid Mechanics 2, and this is the first lecture of this week. We already have discussed about boundary layer, Blasius Solution, and some sort of a turbulent flow, how to deal with the turbulent flow. Today in this boundary layer concept, we will be dealing with the boundary layer thickness. We already have an idea. Another name for that boundary layer thickness is called as disturbance thickness. And then we will introduce one more type of a thickness. We have given a name displacement thickness, and then we will calculate this displacement thickness using the Blasius solution. And then we will go into the another type of thickness called momentum thickness, and similarly we will go into the expression for momentum thickness using the Blasius solution that we already have done. And in the end we will see the relative amount of the displacement and momentum thicknesses for laminar flow over a flat plate. Okay, so the concept of boundary layer thickness is, we already know what Pruntle has described a boundary layer theory, that once you are in the region very much close to the wall. This picture here is an exaggerated picture, but this thickness is a very small distance in the vertical direction, that is in the y direction, where streamlines are slightly deflected away, and this is because of the formation of the boundary layer at the surface. And obviously once fluid enters here and it has to deflect, so what it does is it is required to satisfy what mass is coming in. There is the mass at the outlet should be the same. So it means what happens is this and you know this boundary layer thickness is not just a constant, but it is growing as x increases. So as this x increases, this thickness is also increasing as you are moving from upstream side to this downstream side. And we already have learned in this previous lecture that within this boundary layer, the dominant component of the velocity is in the u direction. The component of the velocity in the y direction is very small in the magnitude, but even though it is small, so that's why this thickness is small, because fluid is not moving in the y direction, fluid is dominantly moving in the x direction. So y component of the velocity is very small, and but is not zero. What you call it disturbance thickness or a boundary layer thickness, we represent by a letter delta, is we don't know. We have already learned it in this previous lecture when we were dealing with turbulence, that there is no such physical boundary available for boundary layer thickness. So this line drawn in the red in this is just a time average of that thickness, which goes this is varying. So what we can see here is what we call it delta. Delta is that distance from this surface to the point where your local velocity u is approaching towards the free stream velocity, and we just mathematically we can say that when u is 0.99 of the free stream velocity, then this distance would be called as boundary layer thickness or displacement thickness. And we already have starting it right from the order analysis. We have the relationship that boundary layer thickness would be directly proportional to x and inversely proportional to the square of the Reynolds number, and from the Blasius solutions this proportionality is becoming an equation, and we know it is something 5.0 is the solution for that boundary layer. So your boundary layer thickness you can exactly work out at any x once you know the Reynolds number. So at a given Reynolds number you have a certain boundary layer thickness. This is something we have already done it. Okay, today we are going to this boundary layer thickness is very important in practical fields. For example, if there is a flow over a hood of a vehicle takes place, then we see very much close to the wall there is a boundary layer thickness that grows. So this thickness is actually very small in that magnitude, but here in this picture it is just shown in quite a big in thickness, but actually it is in reality it is very small thickness. So just for sake of clarity. Okay, now if I ask you to draw the boundary layer of the surface of a car that is a sedan car that is being shown here, and what you need to do is clearly mark out the region in which the boundary layer develops, and the region in which is so-called inviscid region, where the viscous effects are not dominant. So take a pause in this video and try to work out from your copy that how the boundary layer would be on this sedan car. Okay, so take the pause and work out. Okay, I will show you the solution here. The solution is your boundary layer thickness is very thin at this upstream side and at the hood of the vehicle, and that's on the windshield, and then onto the roof, and then we have so this would be the solution, and the boundary layer would be start developing, and then on the rear side of the vehicle there would be a region where eddies and wakes are generated. And so this would be the typical boundary layer, and on the underbody as well, because underbody can be considered as a flat plate. If you think of it as a flat plate, then there is a boundary layer developed onto the underbody as well. So this would be this, and the shaded region is the gray region shown here is the region which is affected by the viscous effects, and what you call it a boundary layer region, including this wake region. And the rest of the things would be as not affected by the viscous effects, so we call it an inviscid flow region. Okay, so now we come to this, see what happens is actually the boundary layer thickness is in reality this boundary layer thickness is much smaller, but just for sake of an exaggeration, always keep in mind this is not a real picture, it is always an exaggeration which shows okay this huge thickness delta compared with y. So quite x is quite large, but delta x is quite small number, small in magnitude. So what you call it once you have a streamline with the uniform flow where the fluid moves with u infinity speed and these streamlines are drawn, and due to this viscous effects what happens is the streamlines have been deflected, and due to this boundary layer this deflection takes place, and the displacement thickness which we represent by delta star is actually the distance that the streamline just outside the boundary layer is deflected due to this boundary layer effect. So the streamlines this deflected by this distance would be called as the since it has been displaced, we call that thickness to be the displacement thickness. So from definition point of view, the displacement thickness is actually the distance by which your solid boundary is displaced in a frictionless flow to give the same mass deficit as exists in the boundary layer. So for example, if you think that you have such a flow in which there is no viscous effect, so it would be inviscid flow, So once you experience a viscous effect, then there is a deflection, and there is a displacement, or the distance by which this solid boundary is displaced compared with the frictionless flow, in order to balance the mass. Then such a thickness is called as displacement thickness. So from this diagram, if you look at, if you have a uniform flow, and in reality you have there is a certain velocity distribution. So u is your local velocity, u infinity is your free stream velocity. And once you say mu is not zero, it means you're talking about not you're talking about a viscous flow. So velocity is not uniform. Velocity would be some function of vertical distance y. So at the y, when y is 0, your velocity is 0, and when your y is approaching towards some distance delta, where your local velocity approach towards the free velocity, then that would be your boundary layer thickness. So typically the velocity profile is like this. So if I am interested in calculating the variation of the velocity as I am moving in the y direction, so at that particular value of y, here velocity is u. So if this is considered to be as a viscous inviscid flow, then the whole velocity would be uniform. So whole velocity would be u infinity, just like this. So the whole flow would be like u infinity, and delta star is hypothetically that distance where you have a certain velocity profile changes due to the viscous effect. And once you have this velocity, so this deficit of the velocity would be, total velocity is u infinity, and here at that particular y, your velocity is u. So this difference is u infinity minus u. So as we move in the y direction, this distance is decreasing, which is changing as y is changing. So what you call it the balance of mass in such a manner that area under the curve, this shaded area, once you have a viscous effect and once you don't have a viscous effect, so your viscosity is considered as 0, then these two shaded areas becomes equal. So once you have that situation, and that ideal distance from this wall is called as displacement thickness. So we just consider a balance of the mass flow rate here. So you see your velocity in this viscous region is at a particular value of y, it is u infinity minus u, and if you take the strip, then the distance of the strip would be dy, and if you multiply by the width of the plate, that is b, so you get the area. So it would be rho u area, that will be your mass flow rate as you are moving in the y direction from 0 to some free stream condition. Infinity is a symbol to use the free stream condition. So if this is this integral is used to represent the mass flow rate when your velocity is varying in the y direction. So this integral would be representing the area under this curve, which is this shaded area. So if this area equals to such a condition in which if there is a uniform flow and so-called inviscid flow, then your velocity would be u infinity, density would be rho, and area would be width times that vertical distance, and here that vertical distance is called as displacement thickness. So from that integral, if you write down delta on the left hand side and everything on the right hand side, so you end up with because rho and rho for cancels out, and you got u infinity minus u over u infinity. U infinity over u infinity would be 1. So 1 minus u over u infinity you are going to get, and b also cancels out. So this free stream condition, we call it approximately when your local velocity approaches towards the free stream velocity. So this limit of that integral would be changed to this so-called disturbance thickness or a boundary layer thickness. So eventually, if you have certain u over u infinity available with you, you can easily work out that displacement thickness, which would be some function of boundary layer thickness, and we will evaluate in the later part of this lecture today. Okay, so this is what our displacement thickness is. And from your Blasius solution, we know if u over u infinity is something, the from your Blasius solution, that u over u infinity is a first derivative of that function with respect to an eta variable, and eta variable is defined in this manner, where y is the vertical distance, which is eta times under root of kinematic viscosity times horizontal distance. So here, in order to what I need is to convert this dy into d eta. So I need to differentiate y with respect to eta. So differentiate y with respect to eta. So it means the whole thing is constant. So it would be just like 2 eta, then it would be this 2. It would be your dy over d eta. So now you substitute all this, you have 1 here, and u over u infinity is the first derivative, and dy would be equal to this multiplier d eta. So dy would be equal to this thing multiplied by d eta. So you have the expression for calculating this boundary layer thickness, displacement thickness, using this Blasius solution. So here this term in this square root is taken out of that integral, because we are integrating with respect to eta. Eta is our variable. As we know from the Blasius solution that if you integrate, so integral of 1 would be eta, and its first derivative would be integral would be its function. So as we know, the derivative and integrals are nothing, just merely an antiderivative. So from this Blasius solution, we know that if you integrate and apply the limits, your upper limit is eta and your lower limit is 0. So for just substitute upper limit, when your eta would be 5, then your eta value is 5 and your function value is 3.28327. So that is what you substituted, the upper limit minus the lower limit. Lower limit is when your eta is 0. When eta is 0, your function is also 0. So that would be 0 minus 0 is here. So once you simplify that expression, so you will end up with the expression for boundary layer thickness, displacement thickness, which is directly proportional to distance x and inversely proportional to the Reynolds number. Just like as boundary layer thickness, the displacement thickness also have that behavior, but instead of 5.0 you have 1.72. so you can compare that displacement thickness is much smaller than your boundary layer thickness. If it is delta over x, it is 5 over the Reynolds number, but here it is not 5 but 1.72 over the square root of that Reynolds number. Okay, so we have learned displacement thickness. Now we go into the momentum thickness. So momentum thickness is just compare the same thing, the situation in which you have inviscid situation and you have a viscous flow, and once you balance the mass flow rate, you end up with a thickness called displacement thickness. In the similar manner, the vertical distance from the wall, if you just balance the momentum, then such a thickness is called as momentum thickness. So displacement thickness is coming because of balancing of the mass flow rate, and momentum thickness is coming because of the balance of the momentum. This because, as you know, as you are moving in this y direction, the velocity is changing. So at every y, for example, at that y you have velocity u infinity minus u. So if you multiply by the mass, then you will be able to get the momentum, and if you apply with the mass flow rate, then you will be able to get the momentum flow rate. So we just do the same thing, just balance the momentum of the flux. So here, as we know, this is the velocity and this would be the area. So rho u area would be the mass flow rate, and I am just multiplying this mass flow rate with the local velocity u, then it would be the momentum flux. So as I am moving in the y direction, this momentum flux is changing because of this velocity distribution and due to this viscous effect. So if ideally we consider what vertical distance that takes place, if it is considered as inviscid flow, once you balance the same area as it is viscous flow, then this resulting vertical distance would be called as momentum thickness, and we use a letter theta to represent that momentum thickness. So rho u and theta a is an area, so that would be momentum flux, and momentum flux is multiplied by velocity, so it would be the mass flow rate times the velocity, then it would be the momentum flow rate, and the momentum flow rate is balanced. So if you just do the same thing, bring theta on the left hand side, everything rho and rho cancels out, and so this is the expression for momentum thickness. We can write exactly for, instead of free stream condition, we say when approximately this momentum thickness would be equal to, your limits would be boundary layer thickness. So eventually the boundary layer thickness, momentum thickness would come out in terms of the boundary layer thickness. Smaller than this momentum thickness we have defined like this. So if we have a knowledge of the velocity profile u over u infinity, and if you integrate it in this y direction, we will be able to calculate this momentum thickness in terms of boundary layer thickness. As we know from Blasius solution, the velocity profile in this laminar flow over a flat plate is looks like that u over u infinity is first derivative, and here eta is some variable which relates with y by this equation. So if I differentiate y with respect to eta, I got this. So now I'm in a position to substitute the value of dy, because dy is this factor multiplied by d eta, and u over u infinity is nothing, just this f prime. So I just substituted here in this momentum equation for momentum thickness, where this u over u infinity is f prime, and 1 minus f prime, and dy is this factor multiplied by d eta. So this integral is a little more complicated to solve because we are not only dealing with the first derivative but the product of the first derivative. So people have solved it numerically, and once they solve it numerically, so they end up with the expression for momentum thickness, which is exactly in the form as we already have seen it for boundary layer thickness. Delta over x was 5 times of Reynolds number, and similarly you have momentum thickness like this. Okay, so now let's compare all these different types of thicknesses. So we have here we have a laminar boundary layer over a flat plate. So we know that from Blasius solution the boundary layer thickness is 5 over square root of the Reynolds number, and the displacement thickness is 1.72 over Reynolds number, and momentum thickness is like this, and we are using by equation 1, 2 and 3 respectively. What I do is now I compare momentum thickness with the displacement thickness. So this displacement thickness with this boundary layer thickness. So I divide equation 2 by equation number 1. So I got cancels Reynolds number and x, and what I end up with just a fraction of the two numbers. So what this fraction says that your magnitude of the displacement thickness would be 0.344 of the boundary layer thickness, or boundary layer thickness obviously would be bigger in magnitude and displacement thickness is smaller. It is only 34.4%, or displacement thickness is the 34.4% of the boundary layer thickness. Similarly, if you divide equation 3 by equation 1, we end up with this ratio which is saying that this ratio is 13.28 times. Momentum thickness is 13.28 times of the boundary layer thickness. So we can say that boundary layer thickness is much bigger, whereas momentum thickness is little bigger, and displacement thickness is little bigger, and momentum thickness is the smallest of these three types of thicknesses. Okay, so these definitions for displacement, momentum thickness allows you to calculate these thicknesses if you just have a knowledge of the velocity profile. For example, in this particular problem, your velocity profile is a function of y over delta, and we have seen in the previous lecture that for viscous sublayer region close to the wall, the velocity profile is a function of y over delta to some power. So the definition for by balancing the momentum, we learned the displacement thickness is this integral. So you just substituted 1 u over u infinity here. So 1 minus u over u infinity over y over delta. Now it is just a simple integral to evaluate, and as I know that the integral of 1 is y, and integral of y to the power half is half plus 1. Half plus 1 is 3 by 2. And similarly, you have delta to the power half is in the denominator, and the constant half plus 1 will be in the denominator, and then just upper limit and lower limit. So you apply the upper limit delta, and our lower limit is 0 here. So in this, for this particular profile, your displacement thickness would be 1/3 of your boundary layer thickness, or you can write like this. Similarly, we can work out the momentum thickness if we have a knowledge of the velocity profile. So here it is better that this is multiplied, and so I've just substituted all the u over u infinity. So just substitute it, and you have an integral in terms of delta. So you just integrate derivative or integral of y to the power half would be y half plus 1, and integral of y would be y square upon 2, and then you substitute the limits. So you got this boundary layer thickness. So this is one of the simplest velocity profile I have taken. So in simple words, if you know the velocity profile, you can work out so easily these displacements.